Hello, everyone. In this presentation, I'll introduce variational cooperative nets, a generative learning framework that combines the strengths of two powerful generative models, the energy-based models and the variational autoencoders. Let's begin with the concept. A variational cooperative net is a framework that integrates the energy-based model, which defines a probability distribution through an energy function, and the variational autoencoder, a top-down latent variable model that enables efficient inference and data generation. In short, the energy-based model captures the underlying data landscape via its energy function, while the variational autoencoder provides an encoder for fast inference of latent variables of the data and a decoder for rapid data generation. Integrating these two types of models will give us better of both worlds. Here's an overview of how the framework works. The energy-based model is learned with the help of a variational autoencoder that acts as an amortized sampler. The training algorithm iterates the following three steps. The first step is ancestral Langevin sampling. In this step, the model generates samples through the variational autoencoder, followed by a finite step of Langevin dynamics. The second step is modified contrastive divergence. In this step, the model updates the energy-based model using both real and generated samples via modified contrastive divergence loss. The third step is variational MCMC teaching, where the variational autoencoder is trained on sampled examples. Why combine these two models? The variational autoencoder offers efficient inference and generation, but tends to have biased likelihood estimation. The energy-based model, on the other hand, can model complex data distributions but struggles with slow sampling due to the iterative process of Langevin dynamics. By training them cooperatively, the variational autoencoder provides a good initialization for the energy-based model sampler, reducing computational cost, while the energy-based model improves the sample quality of the variational autoencoder. This cooperation effectively merges efficiency and expressiveness. Let's first recall the energy-based model. It defines a probability distribution over data through an energy function, assigning lower energy to more likely configurations. The goal is to learn an energy function that accurately differentiates between realistic and unrealistic patterns. Let x be an input image, u of x be an energy function, where we use theta to denote the trainable parameters. An energy-based model is defined as an unnormalized probability density, with z of theta being an intractable normalizing constant. The maximum likelihood estimation of the model parameters is to minimize the negative log likelihood of the observed data by gradient-based optimization. This corresponds to a contrastive loss where the Markov chain Monte Carlo sampling is needed to approximate the computation. The variational autoencoder serves as an amortized sampler in this framework. It generates initial examples, or ancestral samples, from latent variables, providing a starting point for Langevin refinement by the energy-based model. This step is called ancestral Langevin sampling. In the second stage, we update the parameters of the energy-based model. The energy-based model is trained using maximum likelihood estimation, comparing the real data samples with those produced by the ancestral Langevin sampler. This is essentially a modified contrastive divergence learning of energy-based model. In the final step, we update the variational autoencoder through variational MCMC teaching. This process treats the samples generated by the ancestral Langevin sampler as training data for the variational autoencoder, allowing it to learn from these refined examples. In essence, the variational autoencoder absorbs the knowledge distilled by the energy-based model, effectively encoding the energy-based model's knowledge into its latent representation, The training objective of the variational autoencoder in this framework is to minimize the negative log likelihood of the synthesized examples, together with the Kullback-Leibler (KL) divergence between the true posterior distribution and the approximate inference distribution. This learning algorithm seamlessly integrates MCMC teaching and variational inference. Now, let's look at some applications. Variational cooperative nets can be used for image generation and pattern completion. We showcase examples of image generation. Here, you can see examples on different data sets. The model learns from each data set and generates realistic image patterns via ancestral Langevin sampling. Another exciting application is pattern completion or image inpainting. The model can be extended to supervised learning, where the goal is to model the conditional distribution of an output given an input. For example, the input could be a masked image, and the output would be the corresponding complete image. Then, this will become a model for image inpainting. In practice, we achieve this generalization by making both the energy-based model and the variational autoencoder model conditional on the input. These two examples illustrate a comparison between the VCN and several baseline approaches, including those using adversarial learning or variational autoencoder. To summarize, variational cooperative nets integrate an energy-based model and a variational autoencoder into a single cooperative learning framework. The generator from the variational autoencoder and the Langevin sampler from the energy-based model complement each other, improving both efficiency and quality. Through variational MCMC teaching, the framework achieves mutual enhancement between learning and sampling. And as shown, the variational cooperative nets perform effectively in image generation and pattern completion tasks. Thank you.